cloud. Okay. Okay, fantastic. Right. So perfect. Thank you very much, guys. So welcome to the second lecture of the electrodynamics. And so today we will be following up on what we have started, and hopefully we will be closing with green functions, certain green functions that we will be discussing today. Okay, so last time we talked about the electric and magnetic field, and we talked about the charge distribution, and we came to the conclusion that essentially divergence of electric field is not too small. I think it's fine, yes. Divergence of electric field in the electrostatic is given by rho divided by epsilon naught. Curl of B, curl of E is equal to 0. This is a mental health issue, always curl of. Okay, so going for this, so curl of E is equal to 0. And then from essentially we obtain this equation from the fact that electric field is given by minus gradient of the potential. And I mean, we did the calculation and find out that the potential that we had was essentially at the point of x is given by 1 divided by 4 by epsilon naught integral of charge distribution of x prime divided by x minus x prime d3 x prime. So that's the expression that we had in the past. And from these two equations, we found boundaries, or let's say continuity of the field, which essentially from the divergence, we realized that what's going on with the normal of the vector, and from the curl, we find out what's going on with the tangent of the vector. So essentially, we assume that we have a boundary. Here is the, let's say, a region 2, here is a region 1. The normal to the surface is given here, and we have here electric field of 1, and in the other region we have electric field of 2, and then on the surface we have the charge distribution of sigma, which is the charge distribution on the surface. Okay, so from the above equations we find out that for the divergence term we got that E2 minus E1 normal vector is given by sigma divided by epsilon naught, and from the curl equation we got that E2 minus E1 tangent will be equal to 0, and tangent was this vector. Okay, beautiful. So that was essentially what we obtained from the last lecture, and we came to the conclusion that if there is no charge distribution, then the normal of the electric field will be the same in two regions. And also from the curl, we understand that the tangent also is the same. So if there is no charge distribution, essentially, the electric field will be identical in region 1 and region 2. So that was a good, let's say, an important point. And of course, we had during the derivations of these equations, we came to two important relationships as well. So replacing the E from this equation, which is true for electrostatic, into the divergence term, we got that the divergence of minus gradient of phi is equal to, oh, by the way, this is rho divided by epsilon naught. So that the first equation was plus sign, by the way. And here we got that Laplacian of phi is equal to minus rho divided by epsilon naught. Okay. And that was a Poisson equation, which we deal with. And we say that this is extremely important and we will be using. If there is no charge, if there is no charge, which means that rho of x is equal to 0, then we got Laplace equation, which is Laplacian of phi is equal to 0. Okay, so the aim is solving these two. So in a certain point, we will come to this conclusion, and we will come to these equations, and we will be trying to solve these equations. From the mathematics, we got also two important relationships, which was gradient of 1 divided by x minus x prime. The gradient means that these derivative will happen with respect to x. And then we got that will be x minus x prime divided by x minus x prime power of 3. And essentially, we got potential from these relationships. And also Laplacian of 1 divided by x minus x prime, which will be the divergence of gradient of 1 divided by x minus x prime. That was given by minus 4 pi delta of x minus x prime. And we talk about the delta property, delta Dirac property in one-dimensional space, if it's a function of a specific function. And also we talked about the vector property. Okay, so we already discussed about this matter during the last lecture. Today, we will be using this relationship to extend our knowledge about finding electric field in certain space, which when we discuss about that, we mainly focus on finding potential, because electric field is a vector property, and always is good to find the potential. When we find the potential, we take a gradient with a negative sign, we find the electric field. And from the electric field, we understand what's going on with the dynamic, because we can calculate the force. Good. Now, assuming that we are in a region in the space, and in this region in the space, let's say there is a certain region in the space, and in this region we have electric field. Okay, which this electric field, as we discussed, is not a function of time, is only function of position, because we assume electrostatic. And we want to understand what's going on with the force on a particle here. Sorry. What's going on with the force on this particle, which has a charge of Q. What it will be the force on this particle, as we discussed, the force will be given by Q times E, which E is located here. So what's going on with electric field at this given position? And as soon as we have the force, we understand that there is some certain, let's say, movement on that particle. So essentially, if we want to move the particle around, we have to perform some work against this force. Okay, so this is what we will do. So we want to understand what happens if I take this particle and moving around. I want to understand what's going on with the work that I have to perform to move the particle from point A to the point B. Okay, so that's really the goal that we want to do right now. So what the force definitely happens in depending on the charge sign, which is positive or negative, that will be along electric field or in the opposite direction of the electric field. Assuming that the Q is positive, it does not affect the general feature of the calculation. That's just to understand. If the charge Q is positive, then the force will be along this direction, okay? Along the direction of the electric field. So if you put the charge, definitely the charge will start to escape from the region, and it will be along the vector, which is indicated by by red color. However, what I will do, I will apply identical force in opposite direction to keep the particle in the same place. So this is the external force that me as a person, I will apply to the particle to keep it just there. So that the force that I apply, which is external force, it will be minus F that it receives from electrostatic, which is minus QE. With this force, I will keep the particle in the same place. Okay? Then slowly I can move it around along the green curve. I can move it from the position A to the position B, slowly, without having any acceleration. So slowly I will be moving around that region. So essentially, the work that I perform by this action will be, that the work that I apply will be equal to F of external that I do dot dx, which is moving from position A to position B. Okay? Which that force will be equal to minus integral of Q E of the electric field, which we do have there, dot dx from XA to XB. Is that clear? The important point is that you have to have a force identical to electric field force, but in opposite direction, because you don't want to allow any acceleration. That's the important fact. And then I will get minus Q, which is constant, XA, XB, and then electric field, definitely in the electrostatic case, which what we do have, is given by minus gradient of phi, right? So electric field is given by minus gradient of a potential, okay? Dot dx. So then I will have integral of Q with a positive sign, gradient of phi dot dx from XA to XB. Okay, any questions so far, or is clear?
Sorry, can I ask a question?
Yes, of course.
For moving the particle from A to B, we don't need to apply a force that is like along the line, because I don't understand how we are moving the particle while the net force on it is
I will just change the force a little bit, okay, with an epsilon, and then I'm allowing it to control the direction, which direction is moving on. So in order to have a movement, you don't need a force, okay? If you want to move it on a circle, on a path, on a specific trajectory, you need an infinitely small force. I mean, this is what I'm considering, is an infinitely small force. It is not comparable to the QE at all.
But like the work that you're calculating, which is by Fx, that is like, shouldn't it be like on the direction toward, like, opposite direction of E, because we're applying it like that? I mean, I don't understand how this work that you're calculating is exactly the work done by like that a very small force to move from A to B.
This is, so can you repeat your question? Because this is of the force which is against the force of the electric field, which is that value.
Yeah, that's right. But I don't understand how this work by this field is the work that is done for going from A to B.
So then I'll look, what I will do, I will apply the epsilon force here, which epsilon is infinitely small, to allow me to bring it on the path. that I have it without having acceleration. You cannot have acceleration and moving the object around. This is just only due to, I mean, look, I can take a particle, I can move it anywhere around. I'm doing a work, but this work is not due to the field. This work is due to the me. Okay, I want to calculate what's going on with the force due to the electric field, not from me. Okay. Okay. That's the reason that I will apply this infinitely small force just moving around that path. Then I will tend epsilon to be extremely small and 0. Then what I will calculate is just the work due to the electric field, which means that if I take the particle from A to B, what is happening is due to the electric field force. Okay.
Oh, okay. Now I understand. Thank you.
Of course.
Do you even need questions? Yeah. Do you even need to think about it as like the particle moving? Can't because essentially aren't you just calculating the like integrating over every position in between those 2 points?
Yeah, but the point is that you have to take care of the negative sign that you have it here. That's the point.
Right. I know, but I'm saying like essentially you don't even have to think about it as moving. You're just like adding up all the positions where it would be. It doesn't, you know what I mean? Yeah.
Yes, of course you can do that. You can do that. The only things that let's say you can do the mathematics and you will get exactly the same answer. The way that we do the calculation for the force is, or let's say for that specific field force, it has a physical meaning that I was trying to explain the physical meaning of moving on a specific path without having acceleration, but only holding the particle back. So let's say if I'm holding the particle, which has a charge of Q, and the electric field is here and moving the particle in this specific direction. If I leave it, the particle will accelerate in this direction and will escape, right? So I will hold it, but with adjusting my force a little bit, I will allow it to move in a specific trajectory. Okay, then I will keep it there. And this, let's say, adjustment can be infinitely small, so in such a way that it will not affect on anything else. I can take the particle and moving by myself entirely, and that's the work that I will do by myself. It may have also acceleration on the particle, but mathematically you are completely correct, Gavin.
Right. Yeah. So it's like being adiabatic and like thermodynamics sort of thing.
Exactly. The point is having no acceleration.
Okay.
Okay. Perfect. So what is the gradient of phi dot dx?
Dr. Karen.
Yes.
Sorry, can I join with my laptop again? Sorry, can you let me in?
Yes, of course. And I will see people when they are entering. So I have just seen Mahtab joining us. So I let her in. So it's the teaching is a little bit difficult on an online platform because I always have to watch my iPad. I have to also look at the camera and looking at the screen that no one is escaping. Or let's say I don't get the attention of all people. Okay, so let's go. Oops. Ask to mute. Okay, mute this one. Okay, fantastic. So what is the gradient of phi dot dx? So Edith, can we do it together? Let's do it together, okay? You're muted.
Sorry, can you repeat your question?
So what is the gradient of phi dot dx? Let's do it with Edith together, okay? What is the gradient of phi? It will be E1, derivative with respect to 1 of phi, plus E2, derivative with respect to of phi, plus E3, derivative with respect to 3 of phi, right? Dot dx. Dx means that E1 dx1 plus E2 dx2 plus E3 dx3. Do the dot product. So E1, E2, and E3, they are mutually orthogonal to each other. So then I will get derivative with respect to 1 of phi dx1, derivative with respect to 2 of phi dx2, plus derivative with respect to 3 of phi dx3. And this is nothing more than d phi, right? Good. So then the work essentially will be q integral of xa from xa to xb d phi. Good. So the first conclusion is that if xa is equal to xb, let's before doing that. So then from here, I will get that it will be q, and that will be phi at xa or xb. So it means that that will be q times phi at the position of b minus phi at the position of a. Remember that we are moving from a to b. So the first potential is the potential at b, and then the second potential is the potential at a. So it will be q times delta phi, the change in the potential. Okay? So from here, what we understand that if we do the movement on a circle, so we are moving from xa and coming back to the same place, then the work will be if xa is equal to xb, then the work will be 0. Okay? That's a conservative force, essentially. I think last time Gavin asked about the curl of E. What does it mean that it is 0? If the curl of E is equal to 0, this means that the work on a circle will be 0. Or closed loop. Okay? So remember that if that's the electric field and you are moving your particle from this place, you are moving your particle from this place to this place, then if that's has a potential of A, remember this is a scalar quantity. And potential here is xp, then simply the work that you need to do is q, the work that you need to do is q phi b minus phi a. Okay? Any question? And on a loop, it will be 0. Fine? Perfect. So now let's extend it to understand a little bit what is happening with the case that I will have a point charge in space. So what is the potential of a point charge in any position here at the, let's say, location of I don't know, let's call it that's a point charge of q1, and what is the charge, let's call it qi. Okay, that's fine. What is the potential at this point, which is xi? No, let's call it x1. Here is xi. So potential at the position of x1 is given by 1 divided by 4 pi epsilon naught of qi divided by x 1 minus xi. Do you agree with that? That's the potential at the position of this place. So I have a point charge, and I'm looking at the potential in the space around it. Clear? Now I will take another charge, which is Q1 from infinity, and I will bring it here. What is the work that I have to do? What is potential at the infinity?
Zero.
Zero. I will bring it to this place. What is the potential here? Is this potential? Then the work that I have to apply, it will be Q1 times the potential at position of x1, because it comes from infinity. So the first position, which is at infinity, has a potential of 0 minus phi at infinity, which is essentially 0. Then the work is given by Q1 times phi of x1, which is 1 divided by 4 pi epsilon 0 Q1 Qi divided by x1 minus xi. Agreed? Okay, now assume that I have so many of those Qis. I have a lot of them from, I don't know, Qj until Qi, which there are n number of them. So what it will be, the work that I have to apply, it will be again Q1 times the potential due to the charge distribution at position of x1 minus the potential at the infinity. Again, the potential at the infinity is 0. Then when you bring it in, then since the potential is scalar and the field is linear, then what I will get that the total force essentially is given by Q1 times the potential due to all of the charge distribution here. So that will be summation of I to n, I don't know, let's call it from 2 to n of Q, phi of I at position of x1, which at the end, it will be ended up as summation over I from 2 to infinity, or the to n, let's call it, of 1 divided by 4 pi epsilon naught, Q1, Qi, x1 minus xi. Okay?
Are we not taking into account how, if there's other point charges there, that'll affect the potential?
So look, if you expand this, then you will have the potential of 2 from the charge 2, potential from the charge t, potential from the charge n. So all potentials are considered there.
But I guess what I'm saying is if you have, Q1 and then you bring in Q2 and then you bring in Q3 afterwards, isn't Q3 going to be product of Q1 and Q2's potential?
Definitely. I'm not considering the total potential there. I'm considering only the work that is needed to move the Q1 there. I'm not considering what is happening with all charge distribution here. Okay, that's totally correct. So if we want to go, look, this is the total work that happens for the particle number 1. Okay, this is not the total work associated to the charge distribution. Let's go with the scenario that Gavin says. Okay, so assuming that I will move the first particle in, let's move the particle number 1. Do I need to do any work? The space is empty. right? I will move the particle here. No work is needed. Okay, perfect. I move the particle 2 here. What is needed to be done?
We just calculated it before.
Exactly, will be Q2 times phi due to the particle number 1 at position of 2. Okay, so let's call it x1. Let's call these x2. Now I'm moving the third particle, which is Q3. What I have to do? And the position of these is x3. Now already 2 particles are there. I have 2 potentials due to this particle. Then the work will be Q3 times phi1 at the position of 3 plus Q3 potential of 2 at the position of x3. Agreed? So then the total work will be the upper one plus the lower one. Okay, I have now essentially I have to perform 2, let's say, works. One moving particle 2, then moving particle 3, then moving particle 4, particle 5. Then what you have, the number of the potential increases linearly. The first one, it will be 0. The second one will be 1. The third one will be 2 potentials. The fourth one will be 3 potentials, and etc. Essentially, what I have is I'm dealing with a matrix like this, which I have a work due to the 1, 1, which is work of particle 1 on itself, work of particle 1 on 2, work of particle 1 on 3, work of particle 1 on 4, and etc. And then I have work of particle 2 on 1, work of particle 2 on 2, particle 2 on 3, and 2 on 4, and etc. And again, work of particle 3 on 1, particle 3 on 2, particle 3 on 3, and etc. Okay. 3 on 4, and other terms. So essentially, I'm dealing up with a matrix if I fill out all of those terms, and then the only terms that they are showing up in the total force, a total work, is the up diagonal term, which is work due to the particle 1 and 2, 1 and 3, 1 and 4, and etc. Then 2 and 3, 2 and 4, and etc. And until the last one, which will be particle, let's say n and n. Sorry, n and n minus 1. Okay, so this is what happens. So essentially, the total work, which I will do the calculation, will end up with these matrix elements, which we will do the calculation later on. But let's do the mathematics and understanding what is happening. So the first one, the work from moving particle 1 to 1, it will be 0. Work from particle 2 to 1 to 2, which was Q2 phi 1 at x2. Work moving particle 3, which let's call it moving particle 2 here, which will be Q3 phi 1 x3. This is what we call it W31, and that is what we call it W21, plus Q3 phi 2 and x3. This is what I call it W32, and etc. So all of those will be the total work, will be summation of I j qi phi j of xi. Okay, this is the total work that I'm expecting that happens there. Okay. So, and I know that whenever I'm taking the, let's say, the work on particle 3, then I have all lower particles. Let's say I have particle 1 and particle 2 involved. I'm not considering particle 3, particle 4, and particle 5. So there is a condition that J is always below I. If I remove this condition, then I will have 1/2 of I and j of qi phi j of xi. It looks like that. So I'm looking at the matrix. So essentially, I look at the up diagonal term. So I say that I will consider all elements when j is greater than I. Now, I will not consider this, so I will consider also the lower part, but I know that they are symmetric. The matrices are symmetric, so then what I have to do, I have to do sum them, which actually I'm doing the sum twice. Then the total energy will be twice of what I get actually. So that's the reason that I put a coefficient of 2 and I relieve the condition on I and j. So now the summation happens from I and j from 1 to n in the system. Okay, so then replacing the condition, so it will be summation of I and j, qi, and for phi j, I will get qj divided by xi minus xj. So, and 1 divided by 4 pi epsilon naught. So essentially, I will get 1 divided by. Is it clear now, guys? The important point is that I will get a factor of 1 divided by 2. And the reason is clear because here we assume that the j is lower than I. But however, on the second step, I relieve this condition, which means that I'm doing the summation over all elements. Okay. Thumbs up or down, guys? Did you get that? Okay, perfect. This is based on the charge distribution. So it is 1 divided by 8 pi epsilon naught, summation of I and j, qi, qj, divided by xi minus xj. Or remember that we have 1 divided by 2. If you know the potentials, then it will be qi phi j at the position of I. Okay. Now, assuming that you have infinitely small charge distribution of dqi and dqj. So now I have qi and qj. I will replace them with dq and dq prime. Okay. Now I'm changing from a point charges into, let's say, the continuous form. Okay. Which dq essentially is given by rho at x d3x, and for the other one is rho of x prime d3x prime. Clear? So I will assume that now these two charges, or the charge distribution that we assume here, they are, let's say, small charges. So they have a dq, which they are located in a specific space. And let's do the replacement and find out what's going on with the work. So work now is given by 1 divided by 4 pi epsilon naught. Sorry, 8 pi epsilon naught. And the summation, I have 2 summations on I and j. So which means that I have 2 summations on x and x prime. So it will be integral of d d3x integral of d3x prime. Now the charges are replaced by the charge densities. It will be rho of x and rho of x prime divided by x minus x prime. Okay. Or you can look at this way, which means that that is given by 1 divided by 2 integral of d3x of the charge will be rho of x phi of x. You can get that also from these relations. So let me do that. 1 divided by 2 integral of d3x rho x is here. Then I will bring 1 divided by 4 pi epsilon naught into the integral. So I will get 1 divided by 4 pi epsilon naught integral of d3x prime of rho of x prime divided by x minus x prime, which this is the potential at position of x. Good. Any questions, guys? Remember, this formalism is very interesting. I will tell you a little bit more about that in a second. We are dealing with electrostatic, right? So we did not deal with other cases. So in the electrostatic, we know that the divergence of E is given by rho divided by epsilon naught, right? So let's do this. And Laplacian of phi is given by minus rho divided by epsilon naught. From here, I will find out that the rho of x is essentially minus epsilon 0 Laplacian of phi. Good? All right, perfect. So now replace it in the work, total work that we have it for a charge distribution. So if you have a charge distribution on, I don't know, a sphere or on a free form shape, then I will get integral 1 divided by 2 integral of d3x rho of x phi of x. But I know that we are dealing with electrostatic case, then rho can be replaced by minus epsilon 0 Laplacian of phi. Let's do that. So I will get minus epsilon 0 divided by 2 integral of d3x Laplacian of phi times phi. And remember, phi is a function of x, is not a constant. Okay. Good. So let me write it down. Minus epsilon 0 divided by 2 integral of d3x. Okay, so I will write it in this way. Phi. In terms of Laplacian, I will write divergence of gradient. Divergence of gradient of phi d3x. So I will give you a couple of minutes just to think about how to solve these equations, how to simplify it. Any thoughts?
By parts?
Clever. Yes, exactly. We use by parts. Whenever we are stuck, let's go with the by part. Okay. So this will be what I call it du. and this is what I call it V. Oh, by the way, we don't need that. My apologies. And we call these V. So essentially, that will be minus epsilon 0 divided by 2. Then we have UV, right? Minus integral of U dV. So if it's V like that, if the dV is like this, then what is happening with the U will be gradient of phi on the surface, which is it comes with a dot, right? True? Okay. So then what I will get minus epsilon 0 divided by 2. Let's bring it up. Then I will get integral of, gradient of phi normal, which is that n essentially, times phi, minus integral of gradient of phi and then I have also du, which will be again dot gradient of phi d volume, which is d3x. Okay. On the surface. We assume that the charge is localized somewhere, is not extended to infinity. Okay. Then this will be 0 at the surface, and then I will get epsilon 0 divided by 2 integral of gradient of phi power of 2 d3x. What is gradient of phi? Is minus electric field, so E dot E will be E squared minus times minus, it will be plus. So I will get 1 divided by 2 epsilon 0 integral of E squared d3x. And that's a work or energy that you will get it. You have seen that, right? Perfect.
Sorry,
So,
excuse me. What was the argument as to why the first term 0 again?
So we assume that the charge are localized. Okay, so it means that at infinity, which is the surface, where the surface is located, because we do the integral on the entire of the volume. So then we assume when the charge is localized, is not extended to infinity, then that term will be 0. Good. Okay. This assumption we will do very frequently. Fantastic. Okay. So then we do have the work when we want to move the charges around and we keep them in a certain shape. That's the way that you have to do the calculation. You have to find what is going on with the potential there, and then you will take the gradient of this and modulo square, and then you will get the energy. Remember, this energy contains self-energy as well. You have to be very careful with that. So you may get sometimes a paradox in your calculation. And in order to just have a better feeling of this, I will encourage you to do the calculation due to the 2-point charges. Okay, what is happening with 2-point charges, which we just did the calculation? So charge of Q1 and Q2. It is very clear what is the work if the distance between these two is given by x2 minus x1, right? We know how to do the calculation. It will be Q2 times the potential at the position of Q2, right? Now do this based on the above equation. Is that question clear, guys? So the work that we did the calculation, we say that due to the charge Q1, there is no work essentially that you have to do. Due to the charge of Q2, then you have to do a work, and the work is given by Q2 times the potential due to the charge of 1 at the position of x2, which is easy and can be done. Okay, it's only one term. Now we have 2-point charges here. and we want to calculate what is going on with the work here. And we know that the work is given by 1 divided by 2 epsilon 0 integral of e power of 2 d3x. And we know that these point charges, they are delta functions. So you have to put the delta functions in 2 positions and do the electric field, do the calculation of the electric field and find out what's going on there. And you will get a paradox. Do this calculation and tell me for the next meeting, what is the discrepancy between the 2 equations? Clear? Okay. Edith and Tarek, clear?
So you're asking us to essentially find the same equation, but in terms of the electric field?
So if you put 2 charges here, then you get the electric field due to them, right? Replace the electric field here, find the energy, right? And when you find the energy, you will get a discrepancy between the 2. You will get completely different energy. Tell me why. Okay, perfect. Any questions? So far, we only reviewed the electromagnetism that you had in your undergraduate level, with a little bit of more mathematics, honestly, nothing really new. Hereafter, we will deal with something more new and more deep in mathematics. So the first, before going into, let's say, the green functions, we need to learn about 2 theorems, which are called green theorem. Theorem number 1. They are just mathematics, by the way. Assuming that you have 2 functions of psi and phi, they are well-behaved functions, so it means that the derivatives are well-defined. Then I want to calculate what's going on with divergence of psi gradient of phi. What is the result?
Okay, like, should we write take the like derivative of psi and phi, like?
Yes, you have to do that. I will encourage you, I mean, for the next lecture, always having a pen and a paper with yourself. Always do the mathematics by yourself, just to do an exercise. Else, okay. I mean, all of those answers they can be found in in different textbooks, okay, or internet. So it's just we can go with the tricks. So okay. When we go with the divergence means the derivative with respect to all components of I, j, k. So let's do the derivative with respect to 1 or I, okay? Of the field, the same component. So it will be psi gradient of phi, the same component of I. Okay? So what does it mean that it's taking the derivative of psi, and psi is a scalar, gradient of phi, the I component will be derivative with respect to I of phi. Okay, because it's a gradient. So the I component will be the I component, which is I derivatives. So that can be, now you have the derivative of 2 functions will be the derivative of the first one times the derivative of second, and times the second function plus first function times the derivative of the second function. If you write it in the vector formalism, this one is a gradient of psi times gradient of phi. Because both of them, they have the same component. So you are taking derivative with respect to x of phi times the derivative with respect to x of phi. Okay, and then the second one will be psi derivative with respect to x, derivative with respect to x, which will be Laplacian, of course. Laplacian of. Good. So divergence of psi, gradient of phi is gradient of psi dot gradient of phi plus psi Laplacian of phi. Okay. What happened when psi is equal to phi? So then it means that the divergence of phi, gradient of phi, is equal to absolute value of a gradient of phi power of 2, because it's the gradient of phi times that gradient of phi, which will be this, plus phi Laplacian of phi. Okay. Now I can multiply both sides by the volume, and I take the integral of it. So then multiply by d3x and and taking the integral, then I will get integral of divergence of phi gradient of phi d3x is equal to absolute value of gradient of phi power of 2 at d3x plus integral of phi Laplacian of phi d3x. And all of them, they are on volume, on any arbitrary volume that you have, but the volume will be the same. So now, using the Gauss theorem, I will bring the divergence of volume to the surface. So I will get integral of phi, gradient of phi, dot normal to the surface d sigma, and that is on the surface of the volume. So any volume that you do have, it has a surface, closed volume. So then I will get integral of Laplacian of phi power of 2 d3x plus integral of phi Laplacian of phi d3x of the same value. Sometimes we will write it in this way as well. Integral of on the surface of V is in the derivative of V phi. Okay, so gradient times the normal of vector. I will show it with the derivative with respect to n, which we call it vector gradient. Okay, of d sigma equal to power of 2 d3x of volume plus integral phi Laplacian phi d3x of volume. Okay, these are beautiful equation. We call these the first theorem. Okay, green first theorem. I will be using it later on. Let's go with the second theorem. Do you see this equation, guys? Right? Now let's write it when psi and phi, they are swapped. So let's write that. So that's a second theorem. So divergence of psi gradient of phi is equal to gradient of psi dot phi okay, and now I'm swapping the two. I will get gradient of phi, gradient of psi equal to gradient of phi times gradient of psi plus phi Laplacian of psi. Now let's subtract these two together, okay? If you subtract them, you will get divergence of psi, gradient of phi, minus phi, gradient of psi, equal to psi, Laplacian of phi, minus phi, Laplacian of psi. Do you agree? So there is a common term on the right-hand side, which they will cancel out. And remember that the second term is negative, then the term that starts with phi also will be negative. Okay, I'm subtracting these two. Which means that it goes with the negative side. So far, so good? Beautiful. Now I will use the Gauss theorem. I will bring that to the volume, multiply by this by d3x, and I will use the Gauss theorem on the other side. So I will get integral of, in the same fashion. I will not write it down the one step, I will skip it, minus phi gradient of psi dot dn or dot n d sigma is integral of psi Laplacian of phi minus phi Laplacian of psi d3x. That's on the volume. And the other one is on the surface, which creates the volume. Some people, they will write it in this way, integral of derivative with respect, on the surface of volume of V, psi derivative with respect to n of phi minus phi derivative with respect to n of psi d sigma is equal to integral of psi Laplacian phi minus phi Laplacian of psi d3x. This is the second Green theorem. We will be using it a lot. Okay. Any questions? You may ask me why I am doing this sort of calculation. It absolutely has no sense, right? Okay, you will see it. Specifically, the second Green theorem is very useful, and we will do all our calculation based on that. So we always, in electromagnetism, we always deal with divergence and a curl, with boundary conditions. This is what we will do always. So we say that, okay, divergence of E is equal to this, the curl of E is equal to that, divergence of B is equal to this, curl of B is equal to this, and that's what is going on with the electric field and magnetic field on boundaries. Now we prove that there is a mathematical reason behind all this. Okay, so assuming that there is a vector, and this vector I will call it A. This vector, the divergence, which is a scalar quantity, and giving me the source for vector A is known. So the divergence of A, which gives me the source for the vector A, is known in the space, and I call it S function. That can be function of position, okay? And time. I don't care about the time because it's a little bit complicated. And curl of A, which is the C, is also defined in space, okay? Which is the, the curve, essentially. So these two are known, and also A is known on the boundary. So divergence is known, curl also is known everywhere. Okay, so it's a space, and in this space, I know the divergence is known, is as a S, and curl also is well defined. And also I know what is going on with A on the surface of the boundary. Okay. Now, prove to me that A is uniquely defined. The question is that with these conditions that I have, A is unique. If you don't know this, then it doesn't make sense to do the next steps. It absolutely makes no sense.
Can we assume that it's not unique and then prove that it's like?
Go ahead. So let's say that Nazanin says that let us assume that with these conditions, A is not unique. What does it mean? There is another A which has exactly the same property. There is an A prime, which A prime has the following property. Divergence of A prime is exactly the same source. Remember, it's exactly the same function. Curl of A prime is exactly the same function of C, and A is equal to A prime on the boundary. Right? Because they are the same on the boundary. Okay? Which means that are the same at derivative with respect to value. Is that fine? This is what she said. Now what I have to do, Nazanin?
Now it's like we have to find a contradiction or like show that in the end they are equal, like A and A prime. I mean, we have to use these.
Very, very good. So let's go with this way. I will define a vector W, which vector W is A minus A prime. There is a difference between these two, okay? At the end of the day, I have to show that the vector W is 0, okay? Now let's translate what are the property, what are the features of vector W. What's going on with the divergence of W?
It's 0 because it's divergence of A minus divergence of A prime, and they're exactly the same, so it will be 0.
Do you agree, guys? Everyone? Thumbs up or not? Okay. What's going on with the curl of W?
That's also again 0.
Perfect. What's going on with the W at boundary?
It's again 0.
Okay.
Like
W at the boundary is 0. Okay. Do you agree? Guys, agree? No question? Perfect. So now, so it's funny because if I have two functions of a and a prime, which they're satisfying exactly same boundary condition and the same equations for divergence and curl, then any function which is taking the difference between these two will follow these rules, which is the divergence is zero, the curl also is zero. So from the last one, the last expression, I will get that the W is given by minus gradient of a scalar. Right? We just discussed that. Not necessarily is the potential, is the potential associated to this vector of W. It's not that, let's say, electric field potential, is just that vector potential. And the minus sign is just for conservation of energy and etc. So I just, as a habit, I placed there, no need for the minus sign. Good, so it means that this W function, which has this property, can be given by a gradient of a scalar potential. Can we write down the first green function, the first green theorem, which was integral of phi, derivative of phi with respect to n at boundary, d sigma, equal to integral of gradient of phi power of 2 d3x plus on the volume, integral of, I don't remember, what was that? Phi Laplacian of phi d3x. By the way, substituting W into the first equation, which is this one, will give us that Laplacian of phi also is 0. Do you agree? Good. Now let's replace this. So W is given by minus gradient of phi, and also W on the surface or boundary is 0. So what does it mean that also Wn at the surface is 0, which means that derivative with respect to n of phi is 0 as well at the boundary. Do you agree? Laplacian of phi is equal to 0 as well. We just got that from here. Now let's substitute this. So integral of phi, Laplace in a derivative of phi at the surface, d sigma, is equal to integral of gradient of phi is W, so and power of 2, it will be W absolute value on a volume of V is equal to integral of phi Laplacian of phi d3x. What is the Laplacian of phi? Is 0. All right. What is the gradient? What is the gradient of phi at the surface, or the gradient of phi with respect in the direction of n? Is again 0. So at the end, we deal with this equation that integral of W d3x on a volume of V is 0. Good. This is a positive quantity. And volume of V is arbitrary. We don't have any conditions on the boundaries, right? We just say that this function is well defined in the boundaries, and then it's given by specific functions. So when W is positive, and for any arbitrary volume, the integral on that volume will be equal to 0, and we know that W on the surface also is 0, then what we will get, that absolute value of W is equal to 0. Right? What was W? That will give you a W dot W. And we know that the W on the surface is 0. Then from this value, we will get that W is 0 everywhere and not only on the surface. Good? So this means that A is equal to A prime. What you proposed me, Nazanin, is completely correct. So this is the way to show the uniqueness of a function which the divergence and the curl are well defined, and also the function is well defined on the boundary. So now I can relax. I can say that, look, if you give me electric field divergence, electric field curl, and the electric field on the surface or boundary conditions, then I can tell you with 100% the function, and I'm not worried about uniqueness. So whatever that I find to satisfy the boundary condition and satisfy the equations is a solution, is the only solution. Okay, so with this way, I will just relax and I will look for the only solution. Whatever I get as a solution is the solution for me. Okay, now guys, I will stop here. It's almost 25 minutes that we started. I will pause the video and then we will come back in about, let's say 15 minutes, okay? So I hope that you had a nice break. So let's start with a follow-up discussion of the Green's theorem. So so far we have proven that if you know the boundary condition well and you know the divergence and curl of a vector, by the way, very nice cat. I like I like her or him. Then as soon as we know that it's satisfying the boundary condition and we find the vector, then it's unique. There is no other vectors in the world that can satisfy the divergence, the curl, and the boundary condition. Now let's go with the second Green theorem, which I recall well, if I recall well, was something like this. So integral of let's say, should we start with psi? Yes, psi derivative with respect to n of phi minus phi derivative with respect to n of psi d sigma, and that's on the surface, is equal to integral of if it's psi gradient of phi, then it will be Laplacian. So it will be psi Laplacian of phi minus phi Laplacian of psi d3x, that is on the value. Okay, and we just want to clarify and prove that this is really powerful tools for us. Let's consider that in this expression, phi is the potential, okay, electrostatic potential. So phi is the electrostatic potential. Which what do we mean? That Laplacian of phi is given by minus rho divided by epsilon naught. Okay? Is that clear? Good. And on the other hand, And on the other hand, I will assume that psi I will define it for myself, 1 divided by x minus x prime. This is a very useful function, by the way. So what is the property for psi? If you assume this, what is the Laplacian of psi? Which means that you have a Laplacian of 1 divided by x minus x prime. What was the value, Tarek? Minus 4 pi.
Delta of x minus x prime.
Exactly, exactly. Beautiful. So now let's replace it in this expression. Okay, so this is true for any well-defined psi and phi function, and now I'm assuming that psi is the electric field potential, and phi is the electric field potential, and psi is 1 divided by x minus x prime, which has this property. Now replace it here. It will be integral of psi, which is 1 divided by x minus x prime, derivative with respect to n of phi, which is the electric field potential, minus phi, derivative with respect to n of 1 divided by x minus x prime. Okay, p sigma on the surface of v, the derivative of v, integral of volume of v on the volume of v, psi, which is 1 divided by x minus x prime, Laplacian of phi, which is minus rho divided by epsilon naught. Remember, rho is a function, is a charge distribution in space. And then I have minus phi, which I don't know the value, Laplacian of psi, which is minus 4 pi delta of x minus x prime, d3x. Just to make everything more comfortable, let's go that this integral is on the prime, doesn't matter. You will see later on that really doesn't matter, is integral on the psi on phi, but just for the time being, let's assume. Let's do that and let's come back to the original one which we had. Okay, so let's go with the first one. So it will be integral of minus rho of x divided by x minus x prime. We have 1 divided by epsilon naught, d3 of x, minus, it will be plus, integral of 4 pi phi of x, delta of x minus x prime, d3 of x. Okay, good. From the other side, what I have integral of, whenever we have derivative in a direction of n, that can be replaced by gradient of phi dot n x minus x prime minus phi, that will be n dot, what is going on with the gradient of 1 divided by x minus x prime, d sigma. Okay, what I have done, just I expanded the derivative with respect to n is equal to n dot gradient. That's the only things that I have done. Good. So look at this term. what would be the result of these?
4 pi and then add x prime, the potential.
Yes, it will be 4 pi phi of x prime. Do you agree, guys? This is what we derive from also the previous lecture. Any function of x, delta of x minus x0, dx will be the function at x0. This is exactly what happens here. Okay? And integral and delta, they will disappear. What's going on with this one? First of all, what is this integral? Oh, let me write it down. So it will be phi of x prime. I will take away the phi on this side, and then I will bring everything to the other side. Okay? Will be 1 divided by 4 pi epsilon naught. Integral of, there is negative sign, will go away. Plus integral on the surface of V n dot gradient of phi x minus x prime minus phi n dot, what is going on with the gradient of 1 divided by x minus x prime? That's it. We just did the calculation last week, and also this week we repeated again a couple of times. That will be x minus x prime. The result will be a vector divided by x minus x prime power of 3. All right, d3 of x.
Should there be also a minus sign, like?
That is the gradient with respect to x. No, there should not be. Why?
Because I remember that when we did the calculation, the gradient of 1 over x minus x prime was equal to minus x minus x prime over.
No, that was a Laplacian.
Okay, sorry.
No worries. It happens. It happens. So you can just do the derivative. Is the gradient of 1 divided by x, or gradient of 1 divided by r. When you do the derivative, there will be no minus sign. It will be minus 1/2. Again, then there will be another minus sign that appears, which will cancel out each other. Okay. Good. Okay. So the potential everywhere is what I have done. So I assume that phi is the potential and psi is this function. There's no condition here. So it's a volume of V and has a surface, which is a derivative with respect to V. And now what I ended up with is that the potential at any places of x prime is given by this expression, which means that you have to look at the charge distribution. For example, if the charge distribution is here, then you have to look at the distance between these, which is x, and that will be x prime minus x. You do the charge distribution and you do the integration on the volume, which is d3x. And that will be one contribution that will give you the potential. And then there is a contribution due to the surface or boundary contribution, okay? Which is given here. At the boundary, how many terms do we have? 2 terms. One is potential at the boundary, right? and the other one is normal of the potential at the boundary. Okay, is that clear? The integral is on the surface, and then we have two terms. One of them is defining the potential at the boundary, and the other one is defining what is going on with the gradient of the potential at the boundary. Okay, all right or not? Do you agree? Okay, fantastic. So now, assuming that the charges are localized, again, what does it mean? That if I go far away, if the volume is extended to infinity, okay, the surface goes to infinity, then the charges will look like a point charge. And the potential due to the point charge, this is for localized field, localized charges. What I will see that if I'm far away from the charge distribution, I will see it as a point charge. I say this distance is infinity. When I see this let's say charge distribution as a point charge, then the potential here will go like a point charge potential. So which means that it goes 1 divided by r. That will be the potential, right? And also the electric field, which is the gradient of phi, will go with 1 divided by r squared, of course, with a negative sign. I mean, I don't care about the sign. So it's 1 divided by r squared. So therefore, if I look at the term number 2, let's say 1 and term number 2, then the first one goes to be 1 divided by r squared. And the distance that I have, which is 1 divided by x minus x prime, which is the distance from the point charges, or let's say the charge distribution to the point of observation, also will go to be 1 divided by r. Good? So the first term, the gradient will go with 1 divided by r squared, and 1 divided by x minus x prime goes to be 1 divided by r, and r is the distance between the charge distribution and the point of observation. Okay, this is the r essentially. Okay, and also for the other one, for the second term, that goes to be minus the first term, which is potential, goes to be 1 divided by r, right? That goes to be 1 divided by r. What's going on with the second term? This one. That goes to be r divided by r power of 3. So then the entire of this will go to 1 divided by r squared again. Good. So assuming that we are far away from the charge distribution, we are going really far away, then what I will see that the charge distribution now look like a point charge, then the field is going to be 1 divided by r squared, and the scalar potential is going to be 1 divided by r. So the argument or integrand goes to be 1 divided by r power of 3 for both terms. For both terms. All right. And then you are integrating this on a surface. When you integrate it on a surface, what's going on, how the surface will scale if you go far away by a distance of r? No one? Malika?
R squared
Exactly, it will be like a sphere. What is the surface of a sphere? 4 pi r squared. So the scaling for the surface at infinity, an infinitely large, let's say, volume that we assume, it scales up with r squared. That's due to the integral. That's going to be r squared. So the entire both terms, they will scale up with 1 divided by r. Okay? When they scale up with 1 divided by r at infinity or far distances, when r tends to be at infinity, then both surface integrals, they will tend to be 0. Okay? Then what I will get, that phi at x or x prime doesn't matter. I can change the integral now. 1 divided by 4 pi epsilon naught integral of rho of x prime d3 x prime divided by x minus x prime. That's on the bottom. And the other term will go as a function of 1 divided by r, which at r goes to infinity, that will be 0. Okay? So for localized charge distribution, when you bring it to the boundary, then the potential is given by 1 divided by 4 pi epsilon naught integral of the charge distribution divided by x minus x prime d3 x prime. Okay? Remember, where are the boundaries? At infinity. Okay? This is an important factor that you have to consider. What happens when we don't have we don't have this condition that boundaries are at infinity, because we can play with this, then it will be a different scenario. First, I want you to digest this problem clearly, and then we will go to the next step. Is that clear? Any questions? No questions? Okay. Now assume that we don't bring the boundaries to infinity, we will bring the boundaries, we will have arbitrary boundaries. So then we have to deal with these integral, which has 3 terms. 2 on the surface, 1 is it related to the charge distribution. Okay, let me write it down. So that will be, help me if I do mistakes. I'm just swapping x and x prime for simplicity. It's not really a big challenge. You will see later on why easily, without having any worry, I will change the x and x prime. Integral of rho of x prime d3 of x prime divided by x minus x prime. That's on the volume, remember, plus integral on the surface. Oh gosh. Okay, gradient of phi divided by x minus x prime, then x. Okay, so that will be gradient of phi divided by x minus x prime minus x minus x prime phi of x prime x minus x prime power of 3 dot n d sigma prime. Okay, good. That's what I have. So assuming that I have a certain charge distribution, Now I do have certain boundary conditions here. I have different objects. So I may have this cup, which has a certain charge distribution. Then I have metals around myself in my lab, let's say my office. I have my let's say laptop, which is grounded. I have maybe different places also they are grounded. So I have different boundary conditions there. So I'm not allowed to go to infinity and watching at the infinity. So there is boundary condition which is changing. So in this case, then I do have a gradient of phi here. I have also phi here. I have a gradient of phi here and phi here on different places, which they are new or they are boundary conditions. So they are a derivative of volume. They are surface that I'm dealing with. Okay. For example, like you may have a charge distribution close to an infinitely large surface, or a sphere which is grounded, or to a cylinder which is grounded, or to a line which is grounded, and many other problems that you may face in electrostatic. So that's a puzzle. In this case, how do you find the electric field? Let's say, how do you find the potential? Using this formula. And in order to use this formula, you need the charge distribution, which we do have. Also, what we need is gradient of phi and phi, or gradient of phi only, or maybe only phi. Okay, or vice versa. So there are different scenarios that we may go for it. So from this equation, we are getting to the point that gradient of phi or phi or both of them are needed. Where? At the boundary. Okay. So it means that without the surface, without the boundary conditions, we had only the first term, which was integral of rho of x prime divided by this. But now, with boundary conditions, we do have a different potential. This was exactly what Gavin asked. So what is happening? The boundary condition will affect the general expression for the potential that you do have. And our goal for the next two lectures is finding techniques to solve this, to solve different, find potential for different boundary conditions. And that's by itself is a really deep and interesting mathematical approach that not only applies to the, let's say, to electrostatic, but also applies to other cases as well. Even you can apply it to the quantum mechanics. It's a boundary condition problem. You can have it in Schrodinger equation, static Schrodinger equation, time independent. You can have it in the diffusion equation, or you can have it in different scenarios. So that's it. Okay. So now I listed them. I listed you three cases. When gradient of phi dot n is known at the surface. Okay. Or when, let's write it in this way. When derivative with respect to n of phi is known on the boundaries, we call this problem Neumann boundary condition. Okay. Double N boundary condition. And usually I will write with an N capital in my expressions, okay? The second one, which is phi, is known on the boundary. We call this Dirichlet boundary condition. Sometimes happens that you have a mix of phi and derivative of phi dot n, okay, which is n and phi. We call this mixed boundary condition or Cauchy. Okay. And we will express it in different languages right now. Now we will go and we will try to find electric field, not explicitly for 1 divided by x minus x prime, because that is one example that I proposed, but then we will solve it for different boundary conditions. We will start first with the Dirichlet boundary condition, because that happens very frequently in our, let's say, our mathematical formalism and also our problems. Any questions so far? No? I see that Melika is trying to say something. No? Tarek? Tarek, are you okay?
I think so. It's a little stuttery on my end, though.
You mean the internet or the physics? Are you struggling with internet or with the physics? I think he has problem with the internet. Yeah, sorry, Tarek, maybe later on you can watch the video and you will tell
Sorry,
me.
I wasn't able to hear most of you.
No worries at all. Okay, fine, fantastic. So let's go and see. I will go back to the Green's second theorem, and from this we will define what I mean by the Dirichlet boundary condition, and then we will go also with the Neumann boundary condition. Okay, let's concentrate on the Dirichlet boundary condition. Okay, so let's start with the second theorem of Green. So it was psi phi minus phi gradient of psi dot n d sigma equal to integral of psi Laplacian of phi minus phi Laplacian of psi. The 3x, and that's on the volume, that's on the surface. Good. Phi still is the electrostatic potential. Okay, so means that the Laplacian of phi is equal to minus rho divided by epsilon naught. Now psi, we call it Green function. And depending on what is going on with the value of psi at the surface, okay, recall, now we are playing with the psi at the surface. What is happening with the psi? Are we defining normal of psi? I mean, the derivative of n of psi, or we are defining psi at the boundary? Then we do have different problem. If we define psi at the boundary, we call it Dirichlet boundary condition. If we define derivative of psi with respect to n, I will call it Neumann boundary condition. Okay, or maybe if I have many different surfaces, then for some part of that psi is defined, but some part is normal of the psi is defined, then normal of the gradient of psi is defined, then I will call it Cauchy boundary condition. For right now, I will call it Dirichlet, and I will say that psi is defined on the boundary. Okay. For simplicity, I will consider that psi is 0 at the boundary. I can do that, it's my choice. So let's do this. So I will assume that now I don't call it psi anymore. I will call it G of Dirichlet, function of x and x prime. Okay. This is my psi. And what is happening with the psi at the boundary is 0. G of x and x prime at the boundary is 0. Okay, clear? But really, do I call it green function? No, it should have a property. And what is the property? It look like 1 divided by x minus x prime. The property of this is that Laplacian of GD of x and x prime should be equal to minus 4 pi delta of x minus x prime. Okay? And I know that the G is symmetric with respect to swapping of x and x prime. Then that's the condition that you do have it for the green function. So 1 divided by x minus x prime was a green function. Okay? But depending on the problem that I have, then I have to choose if whether that one is just at the surface or not, depending on the situation that we do have. Okay. Any questions so far? Okay, fantastic. Now let's replace it here. Now psi is a GD, and phi is the scalar potential. So I will write it down. It's integral. Oh, sorry. View 100%. Okay. So I will have integral of at the surface or the boundary of GD of x and x prime, gradient of phi minus phi, gradient of g of x and x prime, dot n d sigma is equal to integral of g of x and x prime, Laplacian of phi, well, let's write it down. Laplacian of phi minus phi, Laplacian of g of, all of them, they are d, by the way, of x and x prime, d3 of x. That's on the volume. Good? Okay, now using the properties that I have, this will be replaced by minus rho divided by epsilon naught, and that will be replaced by minus 4 pi delta of x minus x prime. Okay? Good. And what is going on with g at the boundary? Based on the definition that we gave?
0.
0. Let's put it 0. Okay. So let's write it down. So I will get integral of minus phi gradient of GD of x and x prime dot n d sigma equal to integral of, on the volume that's on the surface, of GD of x and x prime minus rho divided by epsilon naught d3 of x. That will be plus integral of 4 pi phi delta of x minus x prime d3 of x. So that, based on the discussion that we had, the phi times the delta Dirac, it will be 4 pi phi of x prime. And from the other side, what I will get a minus 1 divided by epsilon naught integral of rho of x GD of x and x prime d3 of x prime, x plus this one, and other side will be integral of derivative with respect to v of gradient of GD of x and x prime that n d sigma. Okay, so let's write it down. I will take away this integral to the other side divided by 4 pi, then I will get phi of x prime is equal to 1 divided by 4 pi epsilon naught integral of rho of x GD of x and x prime d3 of x plus, no, minus, sorry, minus 1 divided by 4 pi integral of I missed the phi of x gradient of g of t of x and x prime dot n d sigma. Okay, we can simplify further, and based on the discussion that we had previously, I know that g of x and x prime is equal to g of x prime and x, so it's symmetric perfectly. Let me just change the variable, and then I will get this. Phi of x is equal to 1 divided by 4 pi epsilon naught integral of rho of x GD of x and x prime d3 of x prime minus 1 divided by 4 pi integral of phi of x prime, that is derivative of GD x and x prime divided by, and with respect to n prime d2 of x prime. Okay, so for Dirichlet boundary condition, when GD on the surface, remember GD on the surface is 0. Okay, not necessarily the derivative or directional derivatives will be 0. Okay, clear? So that is the relationship that we ended up with. That is a potential for Dirichlet boundary condition. And what we need to do now is finding the green function which satisfy the Dirichlet boundary condition. Okay, so the goal is finding these G or D of X and X prime. As soon as you find this, then it's perfect. You replace it here, you will get the potential. When you know the potential, you know the electric field.
Excuse me.
Yes.
Is it the charge density supposed to be of x prime?
Pardon?
The charge density in the volume integral, is that supposed to be of x prime?
Yes, exactly. Thank you very much. Yes, that should be perfect. Anything else, guys?
Sorry, just to double check, we assume there'll be no phi on the surface, right? Like the phi in the second integral, because like it's bothering me a little bit that we have the same phi.
Yes, perfect. So let's go with this way. It's two sides that you have to pay attention. When we deal with Dirichlet boundary condition, we have to know the green function at the boundary. As soon as we know the green function at the boundary, then we can use this relation. And that also applies that you know what is going on with the phi at the boundary. Okay? So don't get confused. The goal is the green function. As soon as you need the green function, then it's okay. So for example, let me take this. Do you see this notebook? Okay. I will take my, hopefully that doesn't make any noises. I will take this Google Home. I will keep it close to this one. Okay. The Google Home is charged, has a charge distribution. All right. Now this notebook is grounded. It's grounded, so it means that the potential here is 0. All right. So now, assuming that also my room has certain, let's say boundary condition and everything is grounded. What are the potential on the boundaries for all of them? Can you tell me?
Is it 0?
Is 0, right? So the potentials on the boundaries are 0 because they are all ground. Okay, they are at. Now I'm asking you, although I have this boundary condition, what is the potential everywhere? I know only the charge distribution, which is the charge distribution on the Google Home, right? Then you cannot use the simple integral of rho divided by x minus x prime d3 x prime 1 divided by 4 pi epsilon naught. Why? Because there is a boundary condition. The boundary condition changes everything for you. What you have to do is finding a green function, which the green function satisfies the boundary conditions. So when you find the green function, it means that you have to find the green function, which the green function here will be 0. The green function on the other surfaces will be 0. Then you will do the calculation there and you will find out what's going on there. Okay, we will do an example right now, and just to understand how to do the mathematics. Okay, so there are 2 points that you have to pay attention. Is the green function is the main issue, because sometimes you have to keep maybe the potential at a certain constant value. Then when you know the potential at a certain constant value, that potential out of the, let's say, integral will be out, and then you have just only derivative with respect to n of the green function, which you already know the green function that is satisfying the boundary. Okay, good. Hopefully it's clear. So do you want to solve the problem now, or do you want me also to tell you what's going on with the Neumann boundary condition?
Could you quickly explain what happened to the normal when you did a change of variables? I don't understand why it became a fraction.
It becomes fraction?
Yeah, you have it as over del n prime. I don't understand what happened there.
So this is a mathematical formalism that people they use it. So this means that is n prime dot gradient of gd. Okay, this is the notation. People either they write it in this way or they write it in this way. They call it directional derivative. Is it clear, Edith?
Oh, it's just a notation? That's it?
It's just a notation. Yes,
Okay.
it's just a notation, just to not always carrying out n dot gradient of GD. If you don't feel comfortable with that, just write that n dot gradient of GD. So look, when I write derivative with respect to x of f, sometimes I write this. All right. Is that good? Okay. I don't hear you. Sorry. So if you have gradient of f x hat plus y gradient of f with respect to y plus z gradient of f with respect to z dot a specific vector, which is n, let's say nx x hat, ny y hat, and z hat. Okay, this is what we are dealing with. This is essentially gradient of f dot n. We write that in this way. We just write it derivative of n of f, which means that the entire these things. So which means that is nx derivative with respect to x of f, ny derivative with respect to f of y, and z derivative of z of f. The entire of these things, we call it directional derivative.
Yeah, no, thank you.
Pardon?
Huh? I see it now. Thank you.
Okay, of course. It's just a formalism that, you know, mathematicians, they love to simplify things, and that's one form. But in general, it means that it's three derivatives, okay? Or when it's derivative with respect to x, derivative with respect to y, derivative with respect to z, dot product with the vector that you have at the surface, okay? So now tell me if you want to also discuss what's going on with the, oh, we can keep that one just for simplicity. So we can talk about the Neumann boundary condition. I think we do have about 15 minutes. I can tell you about a Neumann boundary condition, and then next week we will go with a couple of examples. So I will solve certain, let's say, boundary conditions with the charge distribution, and then from there you will understand better the meaning of those equations. I think I will leave like that way. Okay. Good. Perfect. Let's go with the Neumann boundary condition. What is the Neumann boundary condition? Exactly the same formalism. You will write the green functions, you will write the green theorem, which is integral of, I think I started with psi, right? Yes, I started with psi. Psi gradient of phi minus phi gradient of psi dot n d sigma, that's on the surface, equal to integral of psi Laplacian of phi minus phi Laplacian of psi d3 of x. Good. For Dirichlet boundary condition, thank you. For Dirichlet boundary condition, we assume that psi is given by g, with g at the boundary is 0. Okay. Now here I will change the formalism. Okay. Again, phi is the scalar potential. which means that the Laplacian of phi is equal to minus rho divided by epsilon naught. And psi is the Neumann green function, or what I call it, the green function that satisfies Neumann boundary condition. And I will label it by g of n of x and x prime, which has the following properties. Okay, one, as soon as we talk about green function, it should satisfy this equation. Minus 4 pi delta of x minus x prime. Good. The second condition is that gn of x and x prime is equal to gn of x prime and x. It's symmetric. Okay. It looks like 1 divided by x minus x prime. Doesn't matter which way do you write it. Now, the Dirichlet boundary condition poses something else. We are not dealing with Gn at the surface. This is Neumann. So we are dealing with derivative of Gn, normal derivative of Gn at the boundary. So we are dealing with derivative of Gn at the surface, okay? Which means that is this n dot gn of x and x prime, or simply, derivative, or simply we are talking about the derivative of gn. Okay, so what it should be the derivative at the surface? What we have done for Dirichlet? We say that the derivative, for the Dirichlet, it was 0, right? The logical sense tells us that we have to use the green function in such a way that it will be 0, the derivative will be 0. No, we cannot do that. We have to go with the condition that the gn at the boundary, the derivative of gn at the boundary is constant. It looks like electric field, right? So at the surface, when we are talking about normal, you may have a charge distribution and normal to the electric field is existent, okay? All right. So that's the condition that we do have, that derivative of gn at the surface, at the boundary, is constant, is not 0 like Dirichlet. All right, now let's replace it here in the Green's theorem and see what is happening. So we will get integral of psi, which is gn of x and x prime, of gradient of phi minus at the surface phi gradient of gn of x and x prime that n d sigma is equal to integral of gn of x and x prime. Laplacian of phi is minus rho divided by epsilon naught minus phi Laplacian of gn, which is again is minus 4 pi delta of x minus x prime d3 of x, and that's our value. Do you agree? All right. So again, that will be minus 1 divided by epsilon naught integral of rho of x, gn of x and x prime, d3 of x prime, that will be plus 4 pi phi of x prime. And the other side will be integral of, on the surface of gn of x and x prime, gradient of phi dot n d sigma minus phi, integral of phi gradient of gn x and x prime dot n d sigma. All right. So I will calculate what's going on with phi of x now, which is dividing both sides by 1 divided by 4 pi, 1 divided by 4 pi, and then taking the other terms to the other side. I will get 1 divided by 4 pi epsilon naught integral of rho of x, gn of x and x prime, d3 of x. Then I have plus, plus integral of gn of x and x prime, derivative with respect to n of phi, d sigma, and then minus integral of, yes, I have 8 minutes, phi gradient of, let's say, let's go with our notation, n of gn of x and x prime, d sigma. Okay.
There should be 1 over 4 pi, so for those two. Right?
Absolutely. Thank you very much for that. I think, did I miss that one also in the previous calculation?
I don't think so.
No, they were there. Yes. Thank you. Thank you very much. So now, so far so good, right?
You're also missing a prime on the first x.
On the first x, yes. Thank you. Thank you very much. Good. Important point is that here we do have a minus sign. Don't forget this. Yeah. And when I take, that will be positive plus minus here. I'll take it to the other side, it will be plus, and the other side has 2 parts, which one is negative sign. Good, fantastic. So, oops, oh, sorry. I tried to move the iPad and then I accidentally pressed the. Yeah, now we are back. Okay. Beautiful. Now, based on Neumann boundary condition, what is this value?
It's a constant, right?
Yeah, it will be out of integral, right? And then that will be integral of phi d sigma. So it will be integral of the potential on a surface, right? I will call this an average potential. That's what it is. So I will call this an average potential. So it will be minus, I don't know if you want to call it phi s. Okay. This is what I do. So indeed, that will becomes 1 divided by 4 pi epsilon naught. And remember, when it's constant, that will be integral on the surface, and of course, integral on the surface of a potential will be again a constant value. That is what I call it the phi s. Okay, and we know that the potential is not important if you shift it by a constant value. That's all. So 1 divided by 4 pi epsilon naught integral of rho of x gn of x and x prime d3 of x plus 1 divided by 4 pi integral on the surface of gn of x and x and x prime, derivative with respect to n of potential, which here is a function of x only, of d sigma plus an average of potential on the surface, a constant. Good. Now, since I will be using it, I use the property of the Green function. I will swap x and x prime, and then let's write the expression. So it will be phi of x 1 divided by 4 pi epsilon naught integral of rho of x prime in gn of x and x prime d3 x prime plus 1 divided by 4 pi integral on the surface of gn of x and x prime, derivative with respect to n prime of phi of x prime d2 of x prime plus a constant.
Sorry,
okay.
Sorry, why aren't you subtracting the average?
Which one?
The average of the potential over the surface. It's minus.
Oh, I didn't want to keep the. It's a constant. Doesn't matter. It's negative or positive. Doesn't matter really. Yeah.
Okay, sure.
Yeah, but you are right. I mean, you have to write it. So, and that is the potential for Neumann boundary condition. Okay. This term is the same for both of them, right? But that term is different. So in the Dirichlet boundary condition, the derivative of Green function appears and the potential on the surface. Here, no, the gradient of potential appears on the boundary condition and the Green function. Okay? So whenever you deal with the potential on the surface, the potential is known at the surface, then it's fine, it's good. You can go with Dirichlet. When the charge distribution is known at the boundary, okay, or normal of the electric field is known at the boundary, then you have to go with Neumann boundary condition. Okay, charge density, because the charge density will be related to the electric field, normal of the electric field. When you know normal of the electric field, that's fine. Then you go with Neumann boundary condition. So now, and we don't talk about the Cauchy because Cauchy is more complicated. For those people that they are interested in Cauchy boundary condition, I will encourage you to look at the Morse and Feshbach mathematical physics book, and that's perfect. It can also help you with other let's say problems that you may have in physics. So I will stop here. It's sharp at 5:20, and next lecture we'll be using these two boundary conditions, and we will be solving different problems. And when we solve different problems, you will have a better feeling about that. But I will encourage you to go through the lectures, through the textbook. Some part of this, what I'm telling you, is not even in your textbook. Go through it and have the better feeling of understanding. If you have questions, just drop me an email, and try to solve also the assignments. Okay, I will stop here. Thank you.